velocity method also we have covered, right? Instantaneous velocity method. Yeah, we have covered that also, and we have solved a problem also on that. Where is that? Yeah, not this one. Yeah. See, this is the instantaneous velocity method. That means this is the instantaneous center for this floating link AC at this instant. And accordingly, we solve this problem also. For example, for a roller, point Q will be the instantaneous center at this instant. Okay, for the entire roller. And velocity at any point on this roller will have a direction. If we join that point to this one, and it will be perpendicular to this direction, and its magnitude will be proportional to its distance from the point Q. Okay, that is the instantaneous center axis. And with that concept, we solve this problem. Okay. So I hope you remember this. Now there is a third method which is called relative velocity method that I am going to cover today. Okay, I hope you can hear me properly. And
Yes, sir.
okay, see, still people are pouring in. Now, what is a relative velocity method? You all know actually from your higher secondary syllabus. If a man is moving within a train with the same direction and as that of the train, the absolute velocity of the man will be algebraic sum of the absolute velocity of the train and the velocity of the man relative to the train. If they move in a same direction, it's very easy. Now, but if there is a change in the direction, then there is a problem. For example, suppose Vc is the velocity of a particle, and V mc is the relative velocity of c with respect to m. Then this will be the velocity of the moving particle m. Vm will be equal to Vc plus Vmc. That we know. Okay. Now this concept, and this is a vectored sum. Okay. We are adding it vectorially. Now, so let us consider a rigid body, okay, which is fixed about this point Q. It is rotating with a angular velocity omega. Okay. Now, some disturbance is coming. Some disturbance is coming.
Anton, mute ko.
Now, suppose if omega is the angular velocity of this entire body about the point Q, then what will be the velocity of the point A? It will be VA. And what will be its magnitude? It will be omega into QA. Okay, where omega is the angular velocity. And what will be its direction? That we know that if I join QA, the direction will be perpendicular to this one. Okay, velocity of the point A will be perpendicular to the line QA along this direction, and its magnitude VA will be equal to omega into QA. Now, what will be the velocity of the point C? It will be VC. It will be parallel to VA actually, and perpendicular to QC. Okay, and its magnitude will be equal to omega into QC. Okay. Now, so if I take a pole Q, okay, where we are indicating the absolute velocity direction from the point Q with some magnitude and direction, then QA represents actually the election time. QA is the, sorry for the disturbance, you cannot help it. QA is the velocity, VA is represented in magnitude and direction because QA is parallel to these directions, okay? And what will be the velocity of the point C? It will be VC. So QC is the velocity of the point C, okay? Both represented both in magnitude and direction. Now, what is CA? What is CA? It's nothing but velocity of the point A with respect to C. That means relative velocity of the point A with respect to C. And what will be its magnitude? It will be in this direction. And you see that this will be parallel to this thing or perpendicular to CA. Okay. Now, what do we mean by relative velocity of A with respect to C? Means that if somebody is sitting on the point C, what he will see as the velocity of A. Okay. It will be at this particular direction, it will be, I mean, it will be shorter than actual velocity of C, A, absolute velocity. And what is the absolute velocity of A? That means somebody is sitting at the point Q. That means who is sitting at the on Earth. Okay, Q is fixed to the Earth. Now, uh, if somebody is sitting on Earth, then what he will see the velocity A, that is the absolute velocity of the point A. And what is the absolute velocity, relative velocity of A with respect to C? Somebody is moving with C, point C. And what he is observing? Velocity of E. So this is the relative velocity. Okay. Now, the same concept, and you will find that what will be its direction of the relative velocity of A with respect to C? It will be perpendicular to the line CA. Okay. So this is the relative velocity. Now let us consider a point B. Okay. Now what will be its uh, velocity direction? Absolute velocity direction. We join QB, and this line represents the absolute velocity direction, perpendicular to this line one. Okay. And what will be its magnitude? Its magnitude will be omega into QB. Okay, no problem. Now, so I can draw in this velocity polygon the absolute velocity of the point B. We start taking, whenever we start anything from for the absolute velocity, it will start from that point Q. That is, we call it the pole. So we'll take a distance QB, which will be equal to, in some scale, the magnitude of the VB, and it will be parallel to the direction of VB. So this will represent the absolute velocity of the point B. Okay. Now I join BA. Okay. I just join BA. And you'll find if you draw it on your own to the scale, you will see that this BA will be actually perpendicular to this distance AB. Okay, it will be perpendicular to this distance. And what is BA represents is the relative velocity of A with respect to B. Okay, so VAB is VA minus VB. And uh, you see that the direction of VAB will be perpendicular to the line AB. It will be, because we are following always the same concept that whenever uh, we see a velocity, we join that point from the other point, and the direction of the velocity will be perpendicular to the line joining them. Now, in case of a relative velocity of A with respect to B is nothing but somebody is sitting on the point B, and he is observing the velocity of the point A. Okay. And its direction will be perpendicular to this line, so this one. And what will be its magnitude? Its magnitude will be this one. Okay, so that it can form this velocity triangle. Any confusion in this regard? Any confusion? Because slowly I'm going in the tougher subjects. Okay.
No, sir.
Okay. No, sir. So we'll with this concept we'll try to solve the problems. That four-bar linkage mechanism problem. See, this is a four-bar linkage mechanism. We already solved this problem by resolution and composition method. See, the point VA is known. That means this omega is known maybe. And the dimensions of all this sides are known. We have to find out the velocity of the point B. Okay. What will be the, this is completely known. VA is completely known. Now, what is VB? VB is nothing but if we use this kind of equations in terms of relative velocity method, VB will be equal to VA plus VBA, relative velocity of absolute velocity of A plus absolute velocity of B with respect to A. Okay. Now, so VA is completely known. I can draw VA. Like we take a Q and QA will be equal to magnitude of the VA, because if the magnitude is given, it will be given. Then, and what will be its direction? Its direction will be parallel to this line or perpendicular to Q2A. Okay. So this is completely known. Now, what is VBA? VBA is relative velocity of the point B with respect to A. Okay. Now, can we find out the velocity of the point B? We can find out. How to find out? We'll use two concepts. One is, uh, do we know the direction of the velocity, absolute velocity of the point B?
So
Yes,
Q to
sir.
gain instantaneous central rotation.
No, I'll go by the absolute velocity, relative velocity method, not
স্যার
absolute.
আমরা স্যার এবি এবি লিঙ্কটার ওমেগাটা পেয়ে যাব
এবি লিঙ্কের ওমেগা পেয়ে যাব কি করে?
স্যার। যেহেতু যেহেতু স্যার ভি এ ভেলোসিটিটা দেওয়া আছে, এই এ পয়েন্টটাও যেহেতু
ভিএ
স্যার এবি।
ভেলোসিটি দেয়া নেই, ভিএ ভেলোসিটি দেয়া
হ্যাঁ
আছে। ওকে, ওকে।
হ্যাঁ, তাহলে স্যার এবি লিঙ্ক, হ্যাঁ স্যার। এবার
এ কিউ,
না মানে স্যার এবি, মানে এবি লিঙ্কটা, এ পয়েন্টটা তো স্যার এবি লিঙ্কটাতেই আছে, তাহলে স্যার এই
না আমি
ভেলোসিটিটা থেকে
আমি
আমরা
আমি
স্যার।
অ্যাকচুয়ালি সি আই উইল ট্রাই টু draw this velocity triangle actually. Okay, we will try to draw
ওকে,
this velocity triangle. Now,
তাহলে
out
স্যার
of
বি পয়েন্টের অ্যাবসলিউট ভেলোসিটি ডিরেকশনটা তো পাবো স্যার। কিউ ফোর
we
বি,
know, right? We know,
কিউ4 বি এর পারপেন্ডিকুলার।
right?
হ্যাঁ
Anything else we know?
স্যার, ভি বি এর ডিরেকশনটাও মনে হয় জানি, সেটা স্যার এ বি
Exactly,
লিঙ্কটার
VBA.
পারপেন্ডিকুলার, সরি।
Yeah, it will be perpendicular to this one
টু এ
from
বি,
the relative
হ্যাঁ
velocity method.
হ্যাঁ
Now,
স্যার।
what we do is from this point Q, I draw the absolute velocity VB direction. I draw a line here, okay, which will be perpendicular to this line, right? And what is the direction of VBA? It will be starting from this one perpendicular to this line. So I take a line which will be perpendicular to this line. I draw a line here. They intersect here. So this gives the absolute velocity of B because it is starting from the pole Q, and this gives the velocity of the point B with respect to point A. That means relative velocity of the B with respect to point A. So this actually gives inter VBA, both magnitude and direction. Got it?
ইয়েস স্যার।
Because we know absolute velocity of direction of the absolute velocity of B. So we draw a line here. We know the direction of the relative velocity of B with respect to A, which is perpendicular to this, and it will start from the point A, definitely. Okay. So we draw a line which will be perpendicular to this one starting from E. They intersect at this point B. So this gives the, this triangle actually represents this one. Now what will be the velocity of the point C? How to find out? This is even easier.
স্যার সি পয়েন্টের রিলেটিভ ভেলোসিটিটা জানি, এ এর রেসপেক্ট আর বি এর রেসপেক্টে দুটোর ক্ষেত্রেই।
ডিরেকশন জানি, নট
হ্যাঁ
রিলেটিভ ভেলোসিটি
ডিরেকশন,
বলতে,
না
হ্যাঁ,
সরি ডিরেকশন, ডিরেকশনটা
ডিরেকশন
জানি
জানি।
স্যার।
তার মানে
সেই ডিরেকশন।
এ থেকে আমি একটা পারপেন্ডিকুলার লাইন টানতে পারি, এর পারপেন্ডিকুলার, which will be this line. Similarly, from BA, BC also we know. VCB also direction we know, which will be perpendicular to this line, right?
ইয়েস স্যার।
Okay, so this line, they intersect at this point. So naturally, this gives the velocity. If I join this one, This gives the velocity of the point C, absolute velocity of the point C. This gives velocity of the point C with respect to A, and this gives velocity of the point C with respect to B. Okay. In fact, I can find out any point in between the velocity, M, say any point. What we do is, you find out this ratio, you divide this line with that ratio and join M to this one. It will give the absolute velocity of the point V. Okay, because those will be proportional. Otherwise, also you can find out with the help of that perpendicular and other thing. Okay. Any problem
স্যার
here?
কিউটা যে কোনো একটা ইনিশিয়াল পয়েন্ট মানে সেটা বলতে চাইছেন, তো সেখান থেকে আমরা প্রত্যেকটা ক্যালকুলেশন করছি
কোনটা
স্যার
কোনটা?
কিউটা, স্যার কিউ যে
And
পয়েন্টটা
Q
যেটা
is the reference point, which is
ফিক্স হলো
with
না।
respect to Earth. What I am seeing, that means any velocity starting from Q gives the absolute velocity, and any other point joining any other point, they are giving relative velocity. For example, this is
স্যার একটা এক্সাম্পল একটু একটু ভেলোসিটি অফ এ উইথ রেসপেক্ট টু বি এটা একটু একবার রিপিট করবেন স্যার, এটা কি করে
okay. Now, say velocity of B with respect to A will be, its direction will be perpendicular to BA always, because any velocity is direction we find. For example, QA is what? Velocity of A with respect to Q2. QT is fixed point, and what is its direction? It's perpendicular to Q2A. The same concept is extended for the relative velocity method also. I mean, velocity of B with respect to A means VBA will be, its direction will be perpendicular to this one, and its magnitude will be equal to actually AB into omega BA. And what will be the omega of this line AB and the length of the side? That actually omega we are not calculating here. You can calculate the omega, and you will find that they will be same. Okay. ঠিক আছে?
স্যার বলছি আরেকবার ছবিটাই যান, বলছি স্যার এইটা এসিবি এটা কি স্যার একটাই লিঙ্ক, মানে হ্যাচ লাইন করা আছে মানে?
হ্যাঁ, এটা একটাই
হ্যাঁ
লিঙ্ক,
স্যার,
সিঙ্গেল লিঙ্ক।
যদি এই হ্যাচ লাইনটা না থাকতো, মানে এটা যদি সিঙ্গেল লিঙ্ক না হতো, তাহলে কি স্যার ভেলোসিটি ট্রায়াঙ্গেলটাই কোনো চেঞ্জ আসতো?
না, কারণ হচ্ছে ভাই কেন চেঞ্জ আসতো না?
স্যার জি
You think about it. See, this is a trivial linkage mechanism. There cannot be any relative motion between them.
ইয়েস স্যার।
AB, BC, and CA, it's a three-bar mechanism. A minimum four-bar linkage mechanism we require to have any relative motion. So, আমি যদি এটা হ্যাচ লাইন নাও থাকতো, মানে যদি এটা তিনটে মেম্বার থাকতো, তাহলেও কিন্তু কোনো রিলেটিভ, এটা সিঙ্গেল অবজেক্ট হিসেবে they would have moved. Okay.
ওকে স্যার।
স্যার এ বি এর আপনি বললেন স্যার পারপেন্ডিকুলার, কিন্তু স্যার আপনি ডিরেকশনটা দেখিয়েছেন অ্যালং দ্য লাইন এ বি, না স্যার?
কোনটা?
মানে ভেলোসিটি অফ এ।
এই লাইনটার কথা বলছো তো?
হ্যাঁ স্যার, হ্যাঁ স্যার।
এটা হচ্ছে এই লাইনের পারপেন্ডিকুলার।
আচ্ছা
তুমি এটাকে এক্সটেন্ড করো, এটা এই
ও
লাইনের
আচ্ছা
এই লাইনটা যেমন, এই যে এই লাইনটা হচ্ছে এই লাইনটার পারপেন্ডিকুলার, এই যে এসি লাইনের পারপেন্ডিকুলার, এই লাইনটা এসি। ওকে, now we'll go a little bit complicated figure. Velocity analysis of a quick return mechanism. Before that, I will let me tell you what is a quick return mechanism. Now, this is a shaping machine. When you will go to the workshop, you will be knowing this is a shaping machine. তোমাদের কি মেশিন ড্রয়িং করানো হয়েছে কি এখনো পর্যন্ত স্টার্ট হয়েছে?
ইয়েস স্যার, শেপার টুল হেড বানানো হয়েছে আমাদের।
টুলেট বানানো হয়েছে, so you know what is a shaping machine. I mean, this is if you don't know, I'll explain. See, this is a shaping machine. Okay, now This is the vice in which we can keep a job here. And this is called the RAM, and this is the tool holder, this is the tool holder, and this is the tool. Now this tool, with the help of this RAM, moves to and fro. It reciprocates basically. And you'll find that there is a sharp edge at the tool here, and the job is not shown here. There is a vice here, the job is held in the vice, and as the tool moves on this, it will cut the material. Okay. Now during the forward motion, because the cutting edge is the forward side, only during the forward motion there will be a cutting. During the backward motion there won't be any cutting. Okay. At the same time, there should be a movement in the sidewise directions. Otherwise, what will happen? It will move at the same line, right? So, what is our objective in a shaping machine is to make a plane. Okay, we uh, cut material during the forward motion. While it is coming back, we give a feed motion with the help of ball and ratchet mechanism, so that this table can shift little bit on the right hand side. Okay, so some new material of the job will come. During the next movement, that material will be removed. As a result, we will get a plane surface with the help of a shaping machine. Okay, now, and there is some gear arrangement to have this to and fro motion, and naturally you will find that the cutting motion is the forward motion. Forward motion is the cutting motion. Backward motion is a idle motion. There is no material is being removed. So this is a lost time actually. Now, machining time, I mean, if you occupy a machine, it's costly because you are losing some time during the backward motion. So what we do basically is that we try to uh, make the backward motion faster than the forward motion, so that idle time will be reduced. How to do it? We do with that, এখানে ওগুলো অত ডিটেলে দেয়া নেই, we do with the help of a quick return mechanism. Why it is called quick return mechanism? Because the return stroke is quicker than the forward one. Now what is a quick return mechanism? This is a quick return mechanism. That means this portion is inside this one. Okay, it's not shown here. Sometimes we do it with the help of a gear, sometimes do it with the help of a um, linkage mechanism. Now, so this is the RAM. Okay, this RAM tool is there. Now this RAM movement is to and fro movement. And what is the quick return mechanism? See, this is a member, okay, which is called a slotted arm member. There is a slot cut here. Within this slot, there is a slider 1 is there. Now the slider 1 is fixed with this link 2. Okay, and this is a fixed point, this is a fixed point. Now this link 2 is rotating continuously. This is rotating. Okay, as it will rotate, what will happen? This slotted bar will reciprocate. I mean, it will oscillate like this. And what will be the two extreme position? And as this will oscillate, when it will come to the left hand side, this will give the maximum left hand positions of the RAM, and when it will come to the right hand side, it will give the maximum right hand positions. So that gives the stroke of the arm. Okay, any question so far?
No, sir.
বুঝতে পারা গেছে? There is a slot cut here. This slotted arm A, as this is rotating continuously, it will pull this slotted arm with the slider. So it will come once in the extreme position on the left side, another time it will come to the extreme position on the right hand side. Now what are the two extreme positions? When this arm will be perpendicular to this one, this line, this center line. This is the two extreme positions. Got it? And here it is the middle position. Okay. Now, what is the advantage of doing this? This link 2 is rotating with a continuous, constant angular velocity, okay, omega. Now, you'll find that from coming from this side, which is one extreme position, to this extreme position, it will take, when it is rotating in the anti-clockwise direction, this link 2 will have a angle theta 2, okay, this angle it will cover. But while coming from here to here on the forward side, it will be forward, no, sorry, reverse side, it will be this angle. Okay. Now, you'll find that this angle is more than this angle. That means during the movement of this one, one will take shorter time, another will take longer time, because omega is constant. So movement from A to B, if it is A and B, okay, B dash to B to rest, whatever you may call it, it will take time what? This angle divided by the omega, and coming from here to here, it will have this angle divided by the same omega. Now, so the time taken by the cutting stroke divided by time taken by the idle stroke will be alpha by beta. Okay. Since alpha and beta are different, so cutting time and the return time will be different. Okay. So naturally, the forward stroke will be slower, reverse stroke will be faster. So this is what we gain with the help of a quick return mechanism. Any question?
স্যার তাতে কি লাভ আছে?
তাতে যেটা লাভ হবে আমার, যে আমি রিটার্ন স্ট্রোকটাকে আমি খুব কম টাইমে করতে পারি। আমার রিটার্ন স্ট্রোক ইজ দ্য আইডল টাইম। ওকে, সো আইডল টাইম উইল বি শর্টার দেন দ্য ফরওয়ার্ড স্ট্রোক। আমি আইডল টাইমটাকে কমাতে চাই মেশিনের। আইডল টাইম কমানো মানে হচ্ছে আই হ্যাভ মোর প্রোডাক্টিভিটি। আমার যদি দুটো টাইমই ইকুয়াল থাকতো তাহলে আমার ওখানে টাইমটা বেশি লস হতো। ওকে, so this is basically a quick return mechanism. Now, and in order to design a mechanism, we need to have the velocity of these points at every instant. What should be the velocity of these points? Now, how to find out those velocities? See, this is a problem given. This is the positions of the quick return mechanism. Can I make it a little larger? Okay. Now, see, we have given different nomenclature. We have to find out the velocity of the point C. Okay. What is given? This omega is given. Omega is given, and all the link lengths are given. If all the link lengths are given, then I can find out, and this angular position is given. What is the position at this instant? We have to find out the velocity at this instant. What is the velocity of the point C? Okay. Not only velocity, actually we have to find out the acceleration also, but we'll go for the acceleration analysis first, and then we'll try to solve that. Now, this is the similar kind of problem we have dealt with in the last classes. Again, we assume 3 points: A2, A3, A4, 3 coincident points belonging to links 2, 3, 3 is the slider, and 4, 4 is the slotted arm. The points A2 and A3 remains always coincident because 2 and 3 are hinge joined. Okay, so as the point A2 is moving, point A3 has to move in the same instant. Okay, so they will have the same velocity naturally. So VA3 will be equal to VA2. There's no problem. Now we try to find out the velocities. So what is the absolute velocity direction will be perpendicular to this one, and magnitude, if we know omega, so omega into the length of the link 2. So this is completely known. VA3 and VA2 is known, and this is the pole O2 and O4, whatever you say. So this is that, this we can draw directly. Okay. Now, what will be the velocity direction of the VA4? This actually we have to draw this triangle. Okay. VA3 will be equal to VA3 or VA2, whatever, will be equal to VA4 plus VA3 with respect to 4. Now, VA4, what is known? The direction is known, which will be perpendicular to this point. So it will be along this direction. So we draw this line. Okay, we draw on one line. And another thing we know is that relative velocity of the point 3 with respect to 4, which is along this sliding direction. So this is known, that direction we know. So what we do is, we draw this line. This is completely known. We draw a line, just draw a line here, okay, which will be perpendicular to this center line. And then we draw another line parallel to this one, starting from this one. So this will intersect here. That will give the point A4. And this is the absolute velocity of the VA4. And this is actually VA3F4. It will be along this direction. Okay. Any confusion? Okay,
No, sir.
now our objective is to find out the point C. So in order to find out the point C, what we do? We find out the point B. What will be the value of the point B? It will be, its magnitude will be perpendicular to this line, and direction will be perpendicular to this line, and magnitude will be this omega into this. Okay, omega we haven't calculated, but we can find out the velocity easily. That means its direction will be along this direction. We find out a point B which will be equal to this proportion. O4B divided by O4, this point, will be equal to this by this. So with this proportion we can find out the point B. Got it? আমি এইখানে বিটাকে ততটাই এক্সটেন্ড করব যাতে ওই প্রপোর্শনে এটাকে এ হয় আর কি, কারণ ভেলোসিটি ডিরেকশন উইল বি প্রপোর্শনাল টু দিস টু ডিস্টেন্সেস. Okay, so we can find out the point B. That means O2B will be given the velocity of the point B with respect to, Earth. Okay, and what will be the velocity? How to find out velocity of C? See, the velocity of C will have absolute velocity direction in this direction because it is guided to move in this direction. Okay, so we draw a line, absolute velocity from here. This line will be horizontal line. Okay, this one. And another velocity direction will be what? Velocity of the point C with respect to B will be perpendicular to this one. So we draw a line from here which will be perpendicular to this one. Where they meet, that gives the point C. Okay, so this gives the velocity of the point C. This is the velocity of the point C with respect to B. This gives the velocity of the point B, absolute velocity. So everything is known. Okay, got it?
Yes, sir.
Okay. Then let us go a little bit complicated problem, but that is theoretical. This part you know actually from your high secondary study. See, this is the path of a particle which is moving along this direction. maybe circular motion about the point 2. At this instant, what is the radius is rho, okay? And what is its velocity is v, which will be perpendicular to this line. So pt is the positions of the point at this instant t. Now at a later instant t plus delta t, p dash is the positions of the point. And oh, this is the velocity at this instant, this is the velocity at this instant. Even it is moving in the constant speed, there will be a change in velocity. Because direction is changing, means there is change in velocity, and it is moving with a constant angular motion and covering a angle delta theta. Okay. Now if I draw these two velocities, what will happen? This is v, which will be parallel to this one. This is v plus delta v parallel to this line. Okay. Now what is the change in velocity? This is the change in velocity dv. Okay. So due to the motion, even with the constant speed, there is a change in velocity, and this change in velocity will give change in velocity. Velocity is dv. So this becomes v plus delta v. This is delta v, and this is v. Okay, and this will be naturally delta theta. Now this del v will have two components actually. One is del v normal, another one is del v tangential component. Now, so how to find out the velocity v? I can, this is, if this is d delta s, okay. So delta s by delta t with limit delta t tends to 0, we'll get the velocity v, okay. So what is del s? S is nothing but rho into delta theta. So basically this will become this one. So ultimately v will be equal to rho into theta dot, or rho into omega, angular velocity. Okay. And in vectorial form, it will be written as, if v will be equal to omega cross rho, where both omega and rho are vector quantities. Okay. Now, and the velocity vector v is always tangential to the path, and its direction is obtained by rotating rho through 90 degree in the sense of omega. If I rotate omega, a rho in the sense omega by 90 degree, that means this 90 degree means along this direction. So that will be give the direction of the v. Okay. This all we know. Now, what will be the the normal and tangential component of acceleration will be what? This is normal component because it has two components, del Vn and del Vt. So del Vn by del t with limit if I take, I'll get the normal component, which will be equal to v into theta dot ultimately. And in vector term, we can represent normal component is omega cross omega into rho, omega cross rho. And what will be the tangential component? This is del Vt with respect to del t, with del t tends to 0. So we'll get ultimately this will be v dot. Okay. Now what is v dot actually? V dot is, v is this one. Okay. So acceleration delta t, if I take with respect to t differentiate it, we'll get delta t will have rho dot theta dot plus rho theta double dot, which is rho dot omega plus rho alpha. Now rho dot is the angular acceleration of the radius vector. Now if it is a circular motion, the rho is constant. Okay. In that case, this portion will be 0. But it might happen that this is not a circular. It is not moving in a circular motion. It is extending slowly. Okay, this radius vector is changing. Then the tangential component have two components basically, rho dot omega plus rho alpha. Now, with this concept, we can find out the relative velocity and relative acceleration. Suppose a link, this link, which is having some motion, both translation motion maybe and rotational motion. So what will be the velocity of the point C with respect to B? Will be omega into BC. Okay, if it has a constant angular velocity. I mean, BC has a constant angular velocity. Now, and VCB will be equal to VC minus VB. Okay, which will be equal to omega into BC. And same link, suppose it is moving with a angular acceleration and angular velocity, omega and alpha. Then what will be its tangential acceleration? Tangential acceleration will be alpha into BC, this one. And normal, it will have a tangential component of acceleration. At the same time, it will have a normal component of acceleration, always. This is towards, from, it will be towards B from C. Okay, so this is called the normal acceleration. And what will be its value? Omega into BC. Okay, so what will be the total acceleration of the point C with respect to B? ACB will be equal to, it will have two component, normal component and tangential component. Normal component will be given by this one. Tangential component will be given by this one. Okay. So, all right.
Yes, sir.
Now, let us go to a little bit more complicated thing. This is basically a part of that quick return mechanism, sort of. Okay. The motion difference between two instantaneously coincident points. In a mechanism, a link is quite guided along a prescribed path in another moving link. For the velocity and acceleration analysis, the difference in the velocities and the acceleration of the two instantaneously coincident points belonging to the two links have to be determined. That means this link 2 having a angular motion which is rotating about the fixed point O, and this link 3 is moving along this direction, okay, with some linear velocity. Okay, so at the instant t, this is the position, and we are again assuming 2 point P2 and P3 coincident point lying on link 2 and link 3, okay, at this instant. Now at a later instant t plus delta t, okay, what will be the positions? It has come here and this link has come here, okay. So there is a displacement actually. The del P2 is the total displacement is del P3 from here to here, the point 3. Now point 3 P3 has come to P3 dash, okay. So del P3 will be equal to P3 prime, this distance, which will be equal to actually del P2 plus delta P3 with respect to 2. That means there is a movement in this direction, at the same time there is a movement in this direction. That gives this delta P3, okay. So this is written here, P2 dash from here to here. This is due to the movement of the link, angular movement of the link, and from here to here due to the linear movement of the link 3. Okay, P2 dash to P3 dash. So we get this value. Now, so how to find out since this is a displacement diagram, displacement position vector, we can find out the velocity. How? We just differentiate with respect to time. So if we differentiate with respect to time, we should get the velocity. So we taking the limit delta t tends to 0, we'll get Vp3 will be equal to Vp2 plus Vp32. Okay, so that we know already. That let me make it a little bit smaller. Okay, that will be better. See, P3, Vp3 is the velocity of the point P3, which is equal to velocity of the point P2 plus velocity of the point P3 with respect to point 2. You already know this thing, okay? Where Vp32 is a vector velocity of the point P3 as seen by an observer attached to the link 2. ঠিক আছে? No problem?
No, sir.
Okay. And the direction of the Vp32 is tangential to the path of P3 in link 2. That means it will be along these directions. Now, similarly, if I am to find out the acceleration, what will happen? I will again differentiate. We should get this one, right? This is the acceleration equation. Vp3 is equal to Vp2 plus AP32. But where AP32 is the acceleration of the point P3 as seen by an observer situated on the link 2. However, this is not correct. It's incorrect because we have to add another term here. Why you have to add another term? If you solve it analytically with the ijk vector, this automatically another term will come here. But I will try to give a heuristic explanation for this. Okay. Now, see what is happening actually. This link has a linear velocity along this direction, always in this direction. Now, when with that rotation of delta theta 2, okay, it has come here. Its linear velocity of this link is always in this direction. So naturally, it should come in at this point. Okay, but what we are finding at it is coming in at this point. Okay, that means it has a displacement perpendicular to its motion. Its motion is in this direction, and this is instantaneous time we are talking about. Okay, so its velocity direction is in this direction, but it will have a lateral movement. Otherwise, it cannot come here. Now, and it has come to shifted laterally by this distance. Now, what is this distance basically? This distance is basically what is this angle? This angle is the same this angle. Okay, and what is this distance? This is the velocity of the point P3 with respect to 2 into that time delta t. That will give this distance, right? And naturally, if we know this distance, what will be the distance? This distance. This distance is this time, this distance into this angle. We give this distance. That has been shown here. AP3 dash will be equal to AP3 dash is this one, which is nothing but this distance into this angle. Okay. So this distance into this angle, this distance is nothing but this velocity into this time. And what is this angle? omega 2, if omega 2 is the angular velocity of the link 2, and if delta t is the time taken by that, then this is the angle. So we are getting, yes. Hmm. 1 minute, I'll take another minute. Okay, another minute or so. Now, so ultimately AP3 dash will be equal to this one. So what is this? This uh, uh, distance is proportional to time square. Now, whenever we find that there is a distance proportional to the time square, that means there is a acceleration taking place in between. Okay. For example, if you say s is equal to half at square, okay, that means a is the acceleration, t square is the time square. So that means there is an acceleration involved in it. And what is the magnitude of that acceleration? If we assume that acceleration is AC, additional acceleration, then half AC delta t square will be equal to this one. So where AC is become equal to this one. Now this acceleration actually, naturally, this acceleration is actually along this direction. That means, in other words, since it has a motion in this direction, the link 2 has a motion in this direction, and there is a movement perpendicular to that direction, that means one additional force is acting on this member. Then only this displacement perpendicular to the motion can take place. And what is this force? That will create some acceleration, and that acceleration is basically AC, which is called Coriolis acceleration, and its magnitude is this one. So ultimately, that extra term we have to take it into account, and this will be the acceleration equation actually. That means AP3 will be equal to AP2 plus AP32 plus AC. This is the Coriolis acceleration. Now, if you analytically solve it vectorially, you will automatically get this Coriolis component. And what will be its direction has been given here. Okay, you go through it. If you have any problem, we'll cover in the next class. Okay, tomorrow.
Okay,
Agi
sir.
pati dichi. So tomorrow there will be a class at 11, right? So we'll take the class at the online mode. Okay, thank you.
Okay, sir. Thank you, sir.
Thank you, sir.
Thank you, sir.